In this example, we've got sand falling on the top of this pile. So it's going blah, blah, blah. And we want to figure out some stuff about it. So first thing I want to think about is what are my variables? So what is going on with a cone? So a cone has different things. There is the volume of that cone. So we'll call that V. We also have the height of the cone, and we also have a radius of a cone. Now we want to try to get the information from the problem into the diagram that I've made. So the first thing that I see is this, that we're adding on to this pile. So the change in my volume with respect to time is equaling 10 meters cubed per minute. We know our height is going to be chilling somewhere like here. We know our radius is going to be over there. And oh, they gave us one of these bits. The pile is going to be 4 meters high at some point. Great. And then there's one more sneaky thing is they've got this. The height of the pile is always 3/8 of the base's diameter. So we know height equals 3/8 times our diameter. And I don't really want to have like diameter and radius. So I'm going to swap diameter out. Diameter is 2 radii. So my height is 3/8 times 2r. So my height is always 3/4 of whatever my radius is. I might need to find out radius. It could be cool to find out radius, but I don't know for sure right now. So I'm just going to call it there. That might be good for right now. If I need to figure out what r is, I will, but I don't know if I need to or not. What do I actually need to find, though? There are two things that we need. We need to figure out how fast is the height changing and how fast is the radius changing. So we need to see the change in our height with respect to time t, and we need to figure out what is changing with our radius with respect to time t. So we need to figure out those two problems inside of this one. Cleaning up my slide a little bit, now I want to write an equation that has something to do with R, H, and volume. Now, we might have this memorized, or a lot of times they give us these equations, especially if it's a weird one like this cone. We get the volume to be this. Here we go. Now I could like start finding the derivative of this, but then I've got like 3 variables and it's going to be pretty tough to figure out what's going on. So instead, what I would like to do is actually substitute in this pink stuff into here because then we'll only have 2 variables and it should be a little bit easier to solve. If we kept both, we'd be trying to solve for too many things at once. So I'm going to rewrite this. Instead of an R, let's put in that 4/3 H squared, just to kind of like clean up my problem a little bit. So now we have, I don't know if I'm going to be more in the way or less in the way there. So that is going to be 16. Let's see, 9 times 3 is 27 pi. Yeah, I'm more in the way. Get out of the way, me. And then h cubed. Okay, so I want to find this thing's derivative with respect to t. So that's dv over dt equals, we're going to drop this 3 in front, and that'll mix with that 27 and cancel. So we'll get 16/9 pi h squared dh over dt using implicit differentiation. Another reason that I'm excited about substituting in that r is I never figured out what r was, and I didn't need to because now I have an equation that just has h in it. We should be able to fill in all of these other values and figure out what dh over dt is, because that's one of the things we're trying to find. So I get this set up. So I've got 16 times 16 is 256 pi over 9 dh dt equals 10. So then I can just divide both sides by 256 pi ninths. So dh over dt equals 90 over 256 pi. Can we simplify that a little bit? Yeah. 45 over 128. Cool. Just for fun. Yeah, just a little bit. Whatever. Okay, so there's our dH over dt. The thing that we still have to figure out, though, is we need to figure out what dr over dt is. So we need to do something with r. Well, hey, we actually did write a little equation that just has r and h in it. And now that we know what h is, or dH over dt is, we could use this thing to kind of do this process one more time. Here's all that figured out, giving you a moment to write that down in your notes. Now, there's something funny about like how they want us to interpret our answer for this. Going back to the original problem, they want us to give our answers in centimeters per minute. Now, everything we've done up to this point has been in meters. So this is telling us what the change is in meters per minute, because everything else has been meters per minute. So we need to multiply both of these by 100 in order to represent our final answer. So I'm going to do that. There we go. And I've written out my sentences, and they became a lot worse when they converted into centimeters. So they were, I don't even know why they wanted to do that. It feels like a weird thing for this question to do, but we do what the problem asks us. So the height of the pile is increasing at 1125 over 32 pi centimeters per minute, and the radius of the pile is increasing at 375 over 8 pi centimeters per minute. We could write those as decimals if we wanted, but I didn't feel like it. Holy crap, I have a whole nother one. I thought that was the last one. In this example, we've got this person running around on a bicycle, and we got this air balloon going up, and they've even indicated on our diagram that there are two things that are moving. So the first thing we need to do is identify what are our variables. The variables we have are the height of the balloon, which is right here, that height. We've got the distance the bike has gone, so that's our distance d here. And then we've got our s of t, which is the distance between our two things. Now we want to put in the information that the problem has given us. So we know that the balloon is moving at a constant rate. So we know dh over dt is going to be 1 foot per second. And we also know that the bicycle is moving at a constant rate. Oh, now I'm going to do dd. Let me just change this to b for bike. So our d bike over dt is 17 feet per second. Finally, there's the distance between the balloon and the bicycle, and that's 3 seconds later. But really, what I want to know what's going on with H and what's going on with B. So if it's 3 seconds later, and originally the first time was at that 65, it's been 3 seconds since then, and the balloon is moving at 1 foot per second. So this height at the time that we're interested in is 68 because it's been 3 seconds since that 65 was recorded. Then the bicycle is moving 17 feet every second. So it was at 0 and then did 17, 17, 17. So that's going to be 51 feet. 51 feet. So B is going to equal 51. Now I've gotten all that information into my graph. The thing I want to figure out is how fast is the distance between the bicycle and the balloon increasing 3 seconds later. So we need to figure out what I'm just going to call it ds over dt. Gotta find that. Transferring my information over, I can tell I need to set up an equation for this. This thing screams right triangle to me, so I'm going to set up a right triangle. Pythagorean theorem thing. I'm going to keep all of these variables because I don't really want to convert any of them into a constant yet, because if I do, then that's going to lock the balloon and it won't grow anymore, and it's going to lock the bike in place and it won't move anymore. So now it's just a matter of differentiating all of those. I've set this up, and so now I'm ready to start substituting, but I can see that there's going to be a problem. I know what H is. I know dH over dt. I know B. I know dB over dt. I know I'm trying to find ds over dt. I don't know what S is. Ugh. Well, Pythagorean theorem, we can figure out what S is at that moment. We're trying to find that change at that moment, but we can figure out actually what that distance is by just plugging that into the Pythagorean theorem. I'm going to plug that in and then plug in my values. Plugging that all into my calculator, I got 85 for that side of S, and then it's just a matter of just some quick simplification of typing all that stuff together, dividing by 2 times 85, and we get 11 for our ds over dt. The final step that we need to do is just interpret what all of this means. So I also typed that up. We would say that 3 seconds after passing under the balloon, the distance between the bike and the balloon is increasing at a rate of 11 feet per second. And I chose 11 feet per second because both of these were given in 11 feet per second, and everything we've been doing have been in feet. Thus is the end of our video on related rates. Keep in mind these 7 steps in order to work through a related rates problem. First, identify what variables you have. Take the time to draw a picture. It really helps organize that information in a way that you can easily tell what's going on and interpret what's happening. Decide what is the rate that you are seeking. What are you trying to find? And then write an equation that you can implicitly differentiate with respect to time t. Finally, substitute your variables. Make sure you do that after you do the derivative. If you do it at the beginning, it locks all of our rates. So we want things to still be moving. So do that after you differentiate. And then finally, write a sentence to interpret what's going on with your problem. Thanks for watching this related rate problems. Hopefully they don't give you too many problems. Hey, bye-bye.